Welcome to the latest installment of Kinetics. In this brief video, I want to talk about reaction mechanisms. Reaction mechanisms all begin with the concept of collision theory. The collision theory is pretty straightforward and relatively simple to understand. The main idea is that molecules have to collide in order for a reaction to take place. That's kind of common sense. Now, those reactions and the collisions that ensue, they must follow some guidelines. Not every collision that takes place is going to result in a chemical change, a merging of the atoms or a breaking up of the molecules, whatever. But for any collision to be fruitful and go toward a reaction, the two conditions are that the collision must be oriented properly. In other words, it has to fit like a jigsaw puzzle appropriately. And the second condition is that those collisions have to have enough energy in order to overcome the activation barrier. The activation energy is not something we've talked of previously, but all that really means is that for any reaction, there's a restriction. There's like a hill you have to top before you can come down to the other side. When two molecules collide, they temporarily form this what's called an activated complex. It's like a combination of all the atoms stuck together in this one mega molecule. That activated complex is very difficult to form. So when the collisions happen, they have to have enough energy to allow that activated complex to form. That's the top of the mountain in the world of kinetics. And then the Arrhenius equation, which we'll look at more when we study temperature effects, the Arrhenius equation kind of goes into some more detail and allows us to quantify these effects. So if you look at this, it's a way to calculate the rate constant. And we have a few variables here. A is the frequency factor. So that's kind of like how often the collisions happen. So each substance usually has a value of A that's determined empirically. And then over here we see absolute temperature, the gas constant, which would be in 8.314 joules per mole K. And then we have the activation energy. So we can see that rate constant is very much dependent on this activation energy and temperature. So we talk about these mechanisms further. We kind of acknowledge now that reactions may not happen in just a single collision. There may be several collisions that need to happen in a certain order or sequence. That's what a mechanism is all about. The steps may be maybe one-step reactions. That does happen. There may be two steps. There may be three steps. There could be innumerable steps in a reaction. But out of all the steps, the one that's the most important is called the rate-determining step, or the slow step, because that one is the one that sets the pace. It's like the pace car in NASCAR racing or something. You can't go any faster than the slowest step in a chemical reaction. That's why it's called rate determining step. The kinetics, the rate laws then are built around that rate determining step. So it's very important, always identify the slow step. We're going to learn here in a bit, but if the slow step comes first, that's awesome. It's very easy. If the slow step does not come first, that makes things a little bit more difficult. And I'll do some examples to drive that home. Now, we look at these steps. We're going to describe our steps in terms of the collision theory. And when we do that, when we describe the steps in a mechanism by the collision theory, they're called elementary steps. An elementary step, elementary implies simplicity, basic concepts, very easy. So the idea in elementary steps is that ever how many things are colliding, that should exactly match your stoichiometry in the step that you're writing out, the chemical reaction that you're writing out. So for example, if I have a reaction that just has one molecule, it doesn't collide with anything, it just, in this case, would have to be like a decomposition reaction. It just breaks apart. We would call that a unimolecular step, and it would be like first order. And then if we have bimolecular, two things have to collide, then it will be like first order in each. And then if it's termolecular, it would be one of the two things have to be doubled or have to be second order, or have to have like two things collide, or you may have three separate things that have to collide all at the same time. So when you have more things that have to collide with the proper orientation, with all the correct amount of energies, the probabilities of that happening become less and less. So termomolecular reactions are actually kind of rare in nature. They do happen, but they're kind of rare. What we do with these elementary steps is that we add them up. And similar to Hess's law, similar to some of the other stuff we've done, we're going to have some things cancel out, but the sum of these elementary steps should add up to equal the overall reaction that you're looking for. So you have to have some idea what you're looking for. Now, when you come up with a mechanism, and people make these up all the time just to kind of take a stab at it, and they go into the lab and try to run some experiments to identify maybe one of the activated complexes. They could see that. And there's lots of things they can do. But the rule that we get out of that is that the mechanism that you make up or come up with has to agree with the experimentally determined rate law. So if we go and do like a crystal violet lab and figure out it's going to be first order, then our mechanism has to predict first order. They have to agree. And then finally, in terms of just some nuts and bolts here, when we're doing mechanisms, we're going to be having to negotiate intermediates and catalysts. So I'll show you some examples of this in a second. But an intermediate, by definition, is a species that is created during one step of a mechanism and is later consumed up in a later step. Overall, the intermediate will not be in the overall reaction. It gets canceled out. Again, that's because it's made by one step and used up in a later step. Catalysts are similar to that in that catalysts don't always show up in the overall reaction. The difference is a catalyst is there at the beginning. It may be used up first, but a catalyst has to be remade because a catalyst does not get canceled out in terms of, let me back that up a little. A catalyst can be in the final reaction. It doesn't have to be, but it at least has to be remade. You can't just disappear like an intermediate does. I'll show you again that's the mechanism and point out the catalyst. All right, so let me show you some examples here. In the first one, the first thing I want to point out is we have two steps to make this reaction. If we add this up, we should be able to add it up to get the proposed overall reaction. So let's do that real quickly. We see the chlorines cancel out. We see then that we can add these two together, NO2Cl, and that gives me 2NO2 plus the Cl2. So this mechanism looks like it could agree. All right, now real quick before I get into answering the actual question for this one, chlorine that canceled out here would be an intermediate. Notice how it is produced in step one, fully consumed in step two. So it does not show up in the overall reaction. That is an intermediate. In this rate law, in this mechanism, the slow step happens first. So that's awesome, because when we write the rate law for this overall reaction, it's just going to depend on the slow step. And it's an elementary step, so the rate will just be the molecularity of NO2Cl in the first step. It's unimolecular. There's only one thing there, so we're going to give it a 1. So now let's look at number 3. Number 3 is going to be different because the fast step is first and the slow step happens later. So what do we do here? Well, the rate law will still be based on that slow step. So we're going to write K, we'll put a K2 here, just to let you know it's the second step in the mechanism. And it will depend on H and CO. This is a bimolecular reaction. A collision has to happen with two things. They're first order in each. So in these, for molecularity, when you write the rate laws for elementary steps, the coefficients do become the exponents. Now, I can't let that be my overall reaction order because it has an intermediate in it. You'll notice that H is produced and later consumed. So I can't have my overall reaction order depending on that. All right, so what we've got to do is solve for that intermediate. I can't have it in there. I'm going to go back to my first step here where the intermediate is produced, and I'm going to write a little relationship. Knowing that this is at equilibrium, because the slow step is second, the fast step is going to go and the products are going to build up, and eventually the reactants will be reformed. It's going to create an equilibrium. So the rate of the forward reaction will be equal to the rate of the reverse reaction. That's a -1 to let you know it's going to be in reverse. So I could write the rate law for the hydrogen being consumed as K1, concentration of H2, all right, unimolecular, equals K-1 times the concentration of H, bimolecular, so exponent 2. And I want to solve that for H. And so I'll divide both sides by K, so, or K-1, so I have K1 over K-1 times the concentration of H2. And to get rid of the squared sign, I'm going to have to take the square root of both sides. So that'll be the square root of the K's, and that means H2 will be to the 1/2 power. And that will equal the concentration of H. Now I can come over here and plug that in for my rate law. So the rate 2 will be K2 times the square root of K1 over K-1 times the concentration of H2 to the 1/2 power, and then we'll have our CO in there to the first order. Now all those K's are just going to combine, so our overall rate law is just going to be rate equals K H2 to the 1/2 and then CO. So that's what we have to do when the slow step is not first.